Good evening, everybody. Can you hear me in the back rows? Just making sure.
Somebody said no, actually.
No. Okay. Well, I'll try to speak up a bit then.
You want to put headset on?
Just plug it in.
This way around, I think. Yeah. Okay. Can you hear me in the back rows now? All right. My name is Erkki Alamäe, and I'm a data scientist at Nortal. And I will talk to you today about what you can do with your data. So first, some introductory words, then a bit about the groundwork of data science, which is cleaning data. Then most of this presentation will be what next, what to do with the clean data, and then finally some tips and tricks about that data volume and computing power. So a few words about me. As data scientists tend to come from different backgrounds. Here's mine. I was a system analyst actually for 7 years. And then about 2 years ago, I discovered the diverse and interesting world of machine learning and data science for myself. So since then, I have been learning and practicing it, basically. I made some assumptions about you as the audience to put together the slide set. I assume that probably you have run SQL queries, NoSQL queries, that you have done data cleaning either manually or using scripting, that you have used spreadsheets, formulas, graphs, but this is where my baseline is, basically. So everything that I think is above that level, I will talk about. Not to bash Excel in any way, because there are also many methods presented here that you can also do with Excel, but that's not the point of this presentation. I will be talking about the methods themselves. Not to bring any fear into this, just to maybe take off some of the pressure. Here is a quote by an author of a book I read recently, and he basically said that at its core, data science is about spotting patterns in data and seeing how one variable affects another. So in no way is it rocket science. The data science process on paper looks like this. You formulate a hypothesis or ask a question. You then acquire data to validate it. You then clean and analyze the data and end up with a result. Well, at least this is how we would like it to be, or how I would also like it to be. But in reality, it's not like this. It's not straightforward, and there is a lot of back and forth between the stages. Another way to visualize it would be to draw a graph where on the one axis you have time, and the other axis you have the number of questions and answers that you have asked and that you have answers for. So based on my experience, the number of answers throughout this project rises. It's not necessarily a linear curve, but it goes up. And the number of questions, when we start, we would like to think that it's a constant, that it doesn't change. But what I have seen is that it rises, and often it rises exponentially. So you usually end up with more questions that you have answers for. And this is the uncertainty. You basically never know what you're going to get when you start out. But it doesn't mean that you won't get anything. And I'm not going to talk about this process at length. This talk is not about that, but when you use the tools that are there, you need to keep in mind that there are sets of assumptions that need to be filled in order to use those tools. And if you make wrong assumptions, then down the line you will make mistakes and you will be using the wrong tools, which will give you the wrong results. Another way to look at the data science process from a helicopter view is that data science is not a Kaggle competition where you have a data set, you do some voodoo magic, and you get a nice predictive model. It is part of data science, true, but everything preceding that, all the work put in before the dataset was published on Kaggle is a lot of work, and some people estimate it to be between 60 and 85% of all the work put in. And already during that stage, a lot of decisions get made. What features do I select? What features mean what? And so on. There is a process that is followed. Granted, it's not deterministic. And there is a toolbox or a set of tools that are used. And just to reiterate, that is not the sexy part of data science, but this is the part that we usually end up spending the most time in. A few more introductory words before we get started. There is no silver bullet. I heard this also mentioned in 2 talks before me, but the good news is that probably each of you have access to some data sets that are not public, that maybe are proprietary to your company, to your wherever you work or who you work for, and that's already a great start. Cleaning data. Cleaning data is required when we have data that has a low signal-to-noise ratio, where it is hard to extract meaning out of it, just without it being processed first. So what is then done is often called by different names. Some names for it are cleaning, pre-processing, data mining, data wrangling. They essentially mean the same thing. So this data, it can be audio, images, log files, databases, scraped websites, you name it. In this form, we cannot use the data directly, but what we do then is called feature engineering or feature extraction, where we, for example, in the case of a log file, we take each row as a row in a table and then start adding columns to it. We extract the features one by one. For text formats, there are many tools to do it. There are specialized libraries for JSON, XML, HTML. For nice log files, you would usually use regular expressions, lots of them possibly. And for ugly file formats, or some, I don't know, custom formats that no one else uses, well, this is when your scripting skills come in. During data cleaning, it is very important to spend as much time as possible cleaning the data and visualizing it at the same time. Getting the distributions, getting to know, getting a gut feeling about the data, For example, finding the average. If we plot a feature on a histogram, we might be tempted to immediately say that, well, let's find the average, which we just calculate it mathematically, and it's this arrow in the middle, that's the average. Whereas if we take an additional feature, use it to highlight the individual distributions within this larger distribution, we now see that we have 3 different normal distributions. And finding averages for these is actually a lot more meaningful than finding the global average, because the global average might not give us anything to work with, or might lead us to down paths that lead nowhere eventually. There are 2 formats used which are kind of equivalent. There is the long format and there is the long format, long and wide, sorry. And, they are semantically equivalent, and you should have no fear about moving between those formats when one step requires it or the other. Usually moving between them is just one single line of code in your data processing pipeline, in your language of choice. This is transformation is called also with different names. It's cast, melt, spread, gather, unfold, fold, depending on the context. Some people just use different names. One thing you will quite often encounter are missing values in data. And here I have just given an example that one option would be to replace it with a median value, where you would just fill in the values based on medians. But this is something where you already need to be very conscious about the decisions that you make, because if you start filling in values, you need to be aware that in the end it might skew your results quite badly. And you might need to come back to this stage actually and choose a different strategy. For example, if the results don't make sense, then you come back to this stage and you choose a different strategy. One method I use quite often is called LOCF, or last observation carried forward, which is used when you have a time series which has sparse values. You might have a value for one date, then 3 days when you have no values, and then again a day where you have a value. If you have reasonable expectation that the value in the middle did not change, you can again use a one-liner to fill in the missing days. Again, this is an assumption that you make that you might need to come back to. And in the more complex cases, the data set might actually require you to fill in values that are not actually there in the data set. Here, for example, we can see that we have joined 2 data sets, one that has a date and one that has a time and value, but none of them are complete. So to make them complete, we have to use custom logic. This is something we again need to have an excuse for, so to say. So in the date column, we have decided that going forward, we will use the date that is given, and going backward, we will look at the time value. If it has changed from 00 to 23, we will assume that it's the previous date. And for the value column, we have done also backwards propagation, not forwards. But this again is an assumption. It might have been done the other way. You will encounter outliers. And again, you need to decide what to do with them. You might have to fix data manually. You might have to go to the data sources to fix it, but usually it's quicker just to do it than during your analysis. But that's not sustainable. So you have to pick a path between those two. In summary, data cleaning is estimated to take up a lot of time of the data science process. It can include fixing data manually. It can actually get long and complicated. And you might need to come back to the decisions that you made. So now, assuming that we have clean data, we are ready to start creating models and to analyze it, not to visualize it anymore. So the tools that can be used. When you don't know a lot about your data, then one method that is used is clustering, where you take data and apply certain algorithms to it that will make subgroups in this data. Clustering helps you understand data and helps you form assumptions. Actually, visually identifying those patterns in 1D, 2D, and 3D is quite easy. Well, you just look and you maybe apply some colors, and already you see groups emerge from the data. But what do you do when you have more than 3 dimensions? Is there a way to compress this 4-dimensional space into something that we can visualize and then find patterns out of it? Well, it turns we can, and let's use an example. This is a classical one. It's a data set of flowers published in the 1930s by a biologist, and it has 4-dimensional data about a species of flowers called iris. The data that is there in the data set is the length and width of the parts of the flowers called sepals and petals. And we will, to demonstrate clustering on this data set, we will use something called PCA, or principal component analysis. Again, by analogy, principal component analysis works like lossy compression. Say you have a bitmap image and you need to do something with it. Well, first off, if this bitmap image is so large that it won't even fit on your hard drive, then you can't do anything with it, basically. You're stuck there. But you might apply lossy compression, for example, to get a JPEG, and then already you get something that you can work with. Similarly, principal component analysis compresses high-dimensional data into lower-dimensional data, or at least it gives you the prerequisite data to do it yourself. By example, this is a data set, 2-dimensional one, that we will apply principal component analysis to. What principal component analysis does, it finds vectors in the data that describe the data best and orders those vectors. So it kind of reorients the axis in the order that allows you to describe the data best. For example, in this case, we got that principal component 1, or PC1, accounts for 99% of the variance. We can see that the dataset has a lot of variability in the diagonal direction, where PC1 is oriented, and PC2 is only 1% of the variance. So based on this, we might decide that, well, hey, let's drop PC2. We don't need it. At least for clustering, we can just drop it and then move on just to PC1. And then we have a 1-dimensional data set. If it were a higher dimensional data set that we got down to 3 dimensions or 2 dimensions, that would already be useful. But this is just to give an example. So applying this principal component analysis on the iris data set gives us that the number of dimensions, as it lessens, this is a graph that shows that how much information do we still get to keep. And we find that if we keep the number of dimensions at 2, then we still keep 95% of the variance of the original data set. When we apply this lossy compression and then decompress back into 4 dimensions, then this is what it would look like visually. So here is the uncompressed data set. Here we have dropped down to 3 dimensions, 2 dimensions, and 1 dimension. Again, 4, 3, 2, 1. So what does this data set look like in 2-dimensional space? It looks like this. And if we draw the dimensions of the original data set in terms of the new PC1 and PC2, this is what we get. We have a feature sepal width, which is quite an important distinguishing feature, and then are all the rest, all the other 3 components, which are kind of similar to each other. Now, having compressed this data 4-dimensional data into 2D, we can start finding clusters. And for example, if we decide that we want to have 2 clusters, this is what it might look like. Or 3 clusters is what it would look like in the middle. And for reference, the original data set, which also had, in addition, the actual species that the flowers were, looks kind of similar. You can see that we have lost a bit of information, and also the choice of clustering algorithm makes a difference. But in essence, this is how we found patterns in 4-dimensional data. And visually, we went from this, where we didn't know how those 3 species are related, to this. So this is 1 species, and these are 2 other species which are kind of similar to each other. Here we showed the example of 4 dimensions, but you can also go higher. For example, this is the so-called MNIST data set consisting of handwritten digits, where each digit is 28 pixel by 28 pixel array, and each value is a grayscale value of that pixel. So in total, each image is 784 values of grayscale. And I didn't do this visualization myself, but actually a machine learning researcher named Christopher Olach did it. And here you can see the unclustered data set, which is, all the numbers are clobbered together. But now if we apply this iterative clustering algorithm, you can see in real time actually how it starts to cluster the numbers. So here, for example, we have the number 1s, here we have the 6s, here we have the 0s, and so on. But it's not pure. There are some which are in the middle of other digits and so on. For example, here we have a 7, which is somehow grouped together with 2s. And this also shows you one method how to find outliers in your data. This takes quite a lot of time, so the author has also shown an image that he obtained by quite a lot of parameter tuning. Well, this is the final result, so to say. And you can see, for example, here a number 5, which is grouped together with the 0s, or a number 3, which is put together with the 6s. And you also kind of get a gut feeling about why, or what makes it look so similar than the others in this group. So this was clustering. You can also do clustering on non-numeric data. For example, shopping basket contents. You find the graph which says that which items are bought frequently together. It's also a clustering problem. It's just that it doesn't involve higher dimensional spaces. Now a few words about anomaly detection. For numeric data, you might come up, for example, with an automatic rule to say that I assume that this distribution is normal, and I will automatically label everything that is, for example, 2 standard deviations more or less than the average as outliers. So here we have done exactly this. We have automatically, based on some assumptions, found some outliers. For time series, some specialized algorithms exist. And here is an example from Twitter's time series anomaly detection algorithm, where it is a multi-stage algorithm where you first find the seasonality of your data. By the way, it has to be seasonal. And then within those seasons, you start finding local anomalies and then global anomalies. For example, we might say that this is around Christmas. Maybe people tweet a lot during Christmas. Or maybe it's New Year's. I actually don't know. And then there's always visual anomaly detection. So you just, you as the researcher or analyst, however you like to call yourself, look at the data visually and try to find which of those values that you have in your dataset are anomalous. It is purely up to your choice, and you have to reason about the choices that you made. But you might, for example, decide that these are the outliers, because they are the farthest from the group center if you look at this dataset visually. Or in the right-hand side, you might consider that this blue flower that somehow ended up in the middle of the green labeled flowers is an anomaly. Maybe it was mislabeled when the data was input. Maybe it was not. Maybe it just was exceptional. In either way, this is something, again, that you might have to come back to later on to revise your assumptions and maybe choose a different strategy. Modeling. Now, this is now something that would be considered sexy, or the sexy part of data science. Modeling, or some call it classification, allows you to fill in the missing values based on previous data. For example, we might predict that the price of an apartment based on rooms and square meters based on previous data. The simplest way to do it is linear regression. You just draw a straight line using a linear algebra method, then pick a spot where you want to get a prediction, and then just pick the point on the line. But there are other techniques as well, and I also heard them mentioned during this first talk about Spark. One of them is decision trees or random forest, if you have many decision trees, where you tell the computer that, well, the solution to my problem should look like this. This is the model that I should have. It should be like a tree. It should involve decision points throughout this decision-making process. And I want you, the computer, to tell me what is the most optimal solution to my problem that would predict my Y column in the best way. Then you go through model training and you get this trained model, which is the set of decisions or the set of parameters decisions that you need to make in this decision tree. A neural net is similar to it, except that you tell the computer that, well, the solution to my problem should have this structure. It should look like a neural net where neurons communicate with each other. Again, you give it an input, an output, and going through training, you get the weights or the parameters of the model. But there needs to be some caution when applying those models. There is the real danger of overfitting, and the overfitting is demonstrated by this green line in the middle. When you train a model to be perfect, then there is the danger that it will start distorting reality. When you have an overfitting model used to influence real life events, for example, if a model would determine someone's salary based on something that they have done in the past, this might really start distorting real life. And in these cases, the best advice that I have read myself is that you should employ human judgment in the decision-making process. Feedback is important, and you need to actually re-evaluate the model periodically. Forecasting is a special case where you are not predicting not just one value, but you are actually predicting many days into the future. And this is useful for time series, again. And forecasting might give you this predicted line and some upper bound and some lower bound, for example. Another specialized kind of algorithm is called process mining, which can be applied to so-called event data, which in a minimum should consist of the process ID or the trace ID, a timestamp, and the step identifier. And if you have data that is formatted like this, you can actually use specialized algorithms to kind of let's say, reverse engineer the process model and start reasoning based on that. So by looking at the model is much more intuitive for a person than looking at the raw data. So that was modeling. Now something called optimization, which is a bit different from modeling because there are a few tricks that you can use with optimization. There is a special class of optimization problems called linear programming. And with linear programming, if the problem is well defined, then actually it turns out that the solution to your problem is one of those corner points A, B, C, D, or E. And you actually can skip evaluating all this parameter space or solution space. But this is only if your problem is formulated in that way. There are also specialized optimization problems for different subdomains, like the vehicle routing problem, which you might define in other contexts as a machine learning problem, but there are specialized algorithms for it. Use them. And lastly, joining two data sets. Although it's not an algorithm at all, or a method that I could give a talk about, it's something that I have found useful personally. Just by linking two data sets, you create a lot of value. For example, you might decide if you have a set of location time series data about vehicles to link it with the locations of nearby, let's say, restaurants or gas stations or police stations, and start finding whether those routes and whether those points of interest have anything in common. A bit about advanced things, and these are things that you can do once you have a trained model. One example would be optical character recognition, where using the trained model you can use the model to derive text from images. Using a special class of neural networks called autoencoders, you can actually do denoising. If you have the trained model and you give it a noisy image, then the model will take the noise away by using its internal compressed representation and then using that in your reverse. It's kind of doing lossy compression and then decompression, that the analogy that we used before. Here is an analogy or use of a trained machine learning model from the domain of raycasting. On the left-hand side, there is this halfway ray-traced image, and the researchers at the graphics card manufacturer NVIDIA found a way to teach the model how to predict what the next pixels would look like. And on the right, you can see the output of that algorithm. And using that trained model, they could speed up the ray tracing process by 4 times. Another thing that can be done is named entity recognition, where the model will tell you whether text contains references to living persons or places in real world. A quite cutting edge example would be generative adversarial networks, or GANs, in other words. And these networks are kind of like making the computer play chess against itself. There are 2 players. One network tries to generate images and the other network tries to say whether those images are real or not. And you end up with these examples here. And these examples all have one thing in common, which is that none of these bedrooms exist. They have been generated by a computer model. Yes, they are based on real life images, but they don't exist in real life. Lastly, a few tips about data volume and computing power. Again, not to bash Excel in any way, but Excel has a hard limit of 1 million rows. On your laptop, you can do 100 million rows or more if you compress and pack data the right way. For example, the Java virtual machine has a 12x overhead for strings, for small strings. For large strings, the overhead is smaller. Once you have packed the data well, then the next option is that use more RAM. Just add more RAM sticks. And lastly, you can work on subsets of the data or samples, and you can parallelize, for example, using Hadoop. And a few words about computing power. When you have a problem that you do infrequently, then 0.01 second versus 1 second doesn't matter. It seems like an instant, but if you have 1 hour versus 100 hours, then already you start thinking how to make it quicker. Especially with large data sets, you need to discover what those dead ends are that lead nowhere and eliminate them as early as possible. And some tricks to do that would to look for optimized libraries. For example, libraries that are specialized for processing graphs. They even might be implemented on GPUs. Another option is using lower level languages, for example C, and then there is the possibility to use GPUs as well for computation. I personally have seen speed ups in the order of 100,000, of which the first 10,000x was achieved just by going to a lower level language, and the last tenfold increase was going from CPU to GPU. Now, granted, it took me quite a while, because the lower you go, the more time it takes, because the lower level it is. But if you have a really large data set, then it might pay off. In the end, it's up to you to decide. And the most important thing is that you need to never lose your ability to iterate quickly as possible, because there will be dead ends. You will need to choose alternate hypotheses, move on with those, and so on. So in summary, we talked about cleaning data, what to do with the clean data, and a few tips about data volume and computing power. Thank you.
Okay, thank you so much, Erkki. We got a few more minutes for some questions to squeeze in. Anybody? Okay, Anton.
I wanted to ask, what is your typical task at work that where you apply all of this?
Every project is different. When I'm asked that how long would a project take, then off the bat I might say that it's 2 weeks. But what happens during those 2 weeks? Probably it's a lot of meetings. Probably it's a lot of getting data.
Well, what do you do? Like, what is your job or assignment to use these things?
Bringing examples of cool results. Good questions.
Well, I can't speak about those, unfortunately, in too much detail.
Yeah, well,
every project is different. It really depends, but I can certainly say that this 60 to 85% rule of data cleaning is real. It does take a considerable amount of my time. Actually, just making visualizations and asking new questions based on answers that I got, asking for additional data from the client. If you're asking about what tools I use,
I'm asking actually an example of where do you apply all of this?
you mean like
What kind of
like
data?
maybe domain area.
domain? I have analyzed industry data, for example, the factory machines, that the sensors that produce a lot of data, all kinds of sensors. Then I have analyzed location data from devices that move around, finding patterns in that. I have done process mining, where the objective is to find the path that takes the longest time, that's the critical path, and then the longer term goal would be to make that path shorter, but first you have to identify it. So those would be 3 examples.
Philip?
Recently, I have noticed that in the news there are a lot of messages about some statistical studies are being rejected. For example, 10 years ago there was some psychology study with some 10,000 of people, and they decided that conclusions are this. But now, 10 years after, they take the same data make data analysis again, and they cannot make the same conclusion. Do you think it could be that bad engineers who analyze the data are responsible, or the scientists who are more responsible for that?
Well, it could be solved if the code that was used to obtain the results was also published along with the research studies. So then it would be actually quite easily be repeated by other researchers. Whether somebody is doing it on purpose just to get published, or whether they made a mistake, is I think is anybody's guess, except for the people who did it.
For example, you're as an engineer, you're doing data cleaning, right? And for example, a client comes to you and say that, oh, please make data cleaning in this kind of particular way to make special results in the end. Do you agree?
Personally, I have not been put in that kind of situation before, but if I would be, then I guess I would say no.
Okay.
One question from there. No, you.
So I have two questions. One is, do you often come across that more granular time-series data will give you better results? Or is it just the question you ask, or just the question you try to get answer for what matters actually? And the second question is about cleaning data. Can you give examples of universally bad collection of data? Meaning, one example, what I've come across is if you want to understand whether a person lives in an apartment or in a house and try to get this out from an address, it's quite difficult because people don't write their addresses in a very clean way. Is there other good examples of not depending on the country, the data is really bad, and it takes a lot of time to work with this?
Okay. So the first question was about whether more granular data helps. Based on my experience, yes, it always does help. And I have seen cases where I have been handed a data set that has already been aggregated. They might think that there are a lot of useful things there. You have the average, you have the median, you have the minimum, the maximum. But it doesn't tell you anything about what happened in the middle in that time period. And that might be the thing you're actually looking for. So in that case, more granular data always helps. And if it's more granular than you need it to be, then you can always apply generalization on your own. The ground rule, I think, in big data is that don't delete it, don't aggregate it, just keep it. And then later apply a schema, analyze it however you might need to analyze it from whatever perspective. And then, like years later, you might decide to clean it, delete it, I mean. So that's my stance on granular data. So. And the second question was, could you maybe repeat it?
So I've come across that it's sometimes like addresses, home addresses are quite unstructured. So people use a house first, then a city, and so on, and some start with the city, and then go to the house, and so on. It's difficult to get out. Are there any other universally unclean data sets that you come across? Not depending on your country, or what can you say that this is going to take time if you see that this is in the data set, or you understand that, okay, probably you're going to have to work with that, and it's very complicated. Are there any good examples? If there are not,
I think addresses are a good example, but you already gave that one.
phone numbers.
Phone numbers, maybe not so much.
Some notes,
My team took part in a hackathon recently where we analyzed the public document registries. which well are there publicly available for all, published by the Estonian municipalities. And well, although everything is there, it's actually everything is different. And if you want to kind of gather it all together and analyze it, then it actually takes a lot of time just to get the data. That's one example where you need to put in a lot of effort to actually get the data. There are no APIs to make your life easier. But I think I'm drawing a blank on the more examples.
Yeah, the guy over there had a question.
So, when we take genes of a person, we are able to derive their facial features by putting in more data. But the reverse is not possible. When we take the facial features of the person, we are unable to derive to the genes, to the entire person. So, this particular problem, one of the leading biotechnology labs of Craig Venter is facing right now, and they have developed their own AI. Is it a standard problem that the things can be solved one side, taking this data set and getting another, but the same techniques cannot be used reversely?
So to sum up, genes can be derived from facial features and not vice versa.
The other way. So if
the
you
other
could
way.
take from a crime spot gene of a person, and you could send it to John Craig Venter's lab, and they could give you exact facial features of the person. But they can't do reverse. Like if you want those facial features and you want changes in your baby, for example, they can't design that.
So the question is how much of a pattern it is that the data can be only derived one way.
Yeah.
I think it's kind of comes down to the domain, whether this mapping between the genes and the facial features is one-to-one. If there is like one facial feature that can come from many combinations of genes, then you can't predict which one of them it's going to be. That's just like the domain-specific part. But I think if we're talking generally, then you can go both ways in the general case. I don't see any objection, because in the one case you would be predicting the genes based on the facial features, and the other case the other way around. It's just a matter of coding or classifying and saying what are the features that you need to predict based on what.
Sorry,
Dmitry has something to add.
Yeah, if I may add, so it's always, if you look at the at information level, right? So from information theory level, there is information from one side and from another, and any process changes the entropy. And if entropy decreases with the process, you can't go back. It's just you've lost some data, and this is the nature of our nature. Like hash algorithm, if you apply hashing function, you can't go back. It's simple as this.
Well, you can look up the hash value from dictionary. But
Maybe a better
Yeah, but there
example
will
is,
be many.
Unless there are collisions.
maybe
Yes.
it's easier to just say that the face is the compression of the cheeks.
Is it an example
Mhm.
of that?
Well, yes, if you have a linear regression model, then the mapping between the y and the x-axis is one-to-one. In that case, the model is, you could say it's purely mathematic, and there is a one-to-one mapping. But it's not always as simple as that. You don't have one feature predicting one another feature. There are quite a lot more.
last question.
An easier question, I guess. What do you recommend, or what advice can you give to somebody that also wants to like dive in all this data science field, I guess?
One book I really enjoyed reading myself was a book called The Data Science Handbook, where the book contains interviews by I think it was 20 or 25 real-life data scientists. And it's not purely technical and it's not purely, I don't know, social sciences, to use that term. But it gives you a really good gut feeling of where the field is and where to start, which directions you might want to go in. Because the field of data science is quite new, then there are not many established bachelor's programs or master's programs. And actually reading what the people have done is, I think, a really great way to get your feet on the ground. And from there on, I think you can already decide for yourself what specific tools you want to start learning first. So the Data Science Handbook, you can get it for free online.
Thank you so much, Erkki. Great talk. Thank you guys for joining us tonight. It was a great pleasure, and we are already planning something for you for November. Stay tuned. Check us out on the internet, Facebook primarily, and see you in a month or so. Thank you.